In simple terms, we can just analyze waves as the propagation of disturbances from one point of a medium to another point of a medium, and that is known as a wave. So when the molecules are crumbled together, there is more concentration there. So it is known as a compressed region or compression region. If both of these quantities are positive in nature, or if both of these quantities are negative in nature, then we say that the wave is traveling in the negative direction. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to start a new chapter here today, and that chapter is waves. So again, you might have seen many waves in our lives, so let's learn the physics behind those waves. So again, to start with, what exactly is a wave? So if you imagine a clear stagnant pond, and if you throw some stone or some object onto that particular pond or into that particular pond, then you can see that the ripples will be forming like this. The ripples will be forming and it will be propagating outwards with an increasing radius. Or again, if you shake a string, if you speak, if you utter a word, everything, there are waves being produced or ripples of disturbances that is being produced. So what exactly is a wave is the answer to that particular question. It is nothing but a disturbance that is propagating through the space-time continuum, or simply we can say that a wave is nothing but a disturbance in the space-time fabric. In simple terms, we can just analyze waves as the propagation of disturbances from one point of a medium to another point of a medium, and that is known as a wave. That can be in the medium that is air right now, and the waves that are reaching you are the sound waves. Right, and again, there are electromagnetic waves that is traveling through this particular room and into your eyes right now, and there is also waves of other forms, that is sound waves are there, mechanical waves are there, vibrational waves are there, and even sea waves are there, right? So many kinds of waves are there. So let's study what is the physics behind all of these different kind of waves. But for that, we need to identify what are the types of waves first. So wave is nothing but a disturbance that is propagating through space and time. Now let's see what are the various types of waves. So again, a wave can be classified into two main categories. That is mechanical waves and non-mechanical waves. So what is this mechanical and non-mechanical waves? Just as I told you that there are various types of waves, it can be mainly classified into two separate categories. The classification is based on how they can actually propagate in a medium, or much more clearer, is there a medium of propagation? That is electromagnetic waves, that is the waves that are coming from the sun. For example, X-rays, gamma rays, UV rays, visible light, radio waves, microwaves, all these waves are a part of the electromagnetic spectrum. So does these waves actually require a medium to propagate? The answer is no, because it is propagating through water, it is propagating through air, it is propagating through the vacuum of space. Exactly, in future classes you will study that space is not vacuum. There are quantum fluctuations happening and all that, but for now imagine that the space is completely vacuum and there is nothing there. So again, if there is no medium also, the waves are traveling. So it means that some waves do not require a medium to propagate, but while other waves actually need a medium to propagate. For example, you can hear me when I speak to you on planet Earth like this because there is a medium of air present. If I am out in space and I'm speaking, you can't hear me because the sound waves cannot travel without any medium, right? Because it's space, there is nothing there. The sound waves that I make, the vibrations that I make are not reaching your ears in space. So there are waves which require a medium to travel and there are waves which do not require a medium to propagate. So based on that, the waves can be classified into mechanical and non-mechanical waves. So mechanical waves are the waves which require a medium to travel. So medium is required for mechanical waves to travel. So medium is required. And non-mechanical waves, no medium is required. So, for non-mechanical waves, there is no need of a medium for the waves to actually propagate through space and time. And again, if you want an example for these, you can just use, pressure waves, sound waves. Like this, any wave will be an example for mechanical wave, and just like that, for non-mechanical waves, you can take any transverse wave. That is, all non-mechanical waves are transverse in nature, and you can take all the EM waves. That is, X-rays, microwaves, radio waves, any EM wave you take, that will be an example for non-mechanical waves, and they will be transverse in nature. Bringing to that, what exactly is that transverse waves? So you studied what are mechanical and non-mechanical waves, but in that there are further categories known as transverse and longitudinal waves. So again, I'm going to categorize these waves into transverse and longitudinal waves. Transverse and longitudinal waves. So what exactly is that transverse and longitudinal waves? So you might have studied in lower classes that sound is a longitudinal wave. So what exactly does that mean? So let's see that. So again, what exactly are longitudinal and transverse waves? So we can define transverse waves as in which the particles will be vibrating perpendicular to the direction of propagation of the wave. That is, if the wave is traveling in this particular direction, the particles in the medium will be vibrating up and down. To imagine that, you can just visualize how a boat will be rocked in sea. Even though the waves are there in the sea, that is in the middle of the sea, the waves are still there. If you stop paddling, the boat will still stay there. The boat will not be moving, because the particles in that particular sea is only moving up and down, because the waves in the middle of the sea is actually transverse in nature, which means that the particles are actually just moving up and down and not forward. So you can actually say that in transverse wave, energy is carried out, but there is no actual displacement of particles that is taking place. The particles are only moving up and down, or simply perpendicular to the direction of propagation of the waves. And you can also see that the transverse wave is propagating like this, that is in the form of a sine or cosine wave. That is, it is having crests and troughs, and it is very important to know that there is no transfer or displacement of particles along the wave. Only particles are moving up and down along the amplitude. And again, only energy is being transferred, or simply energy is only transported in this particular wave. And here longitudinal waves, the example is sound waves. Sound waves are actually the particles are moving parallel to the propagation of the wave. That is, instead of actual motion that is in longitudinal wave, when we speak, I'll take the example of sound waves. So when I speak, the voice that is coming out, that is the vibrations that are coming out of my mouth, is pushing the air molecules. So the air molecule actually hits the molecule right in front of it, and the next molecule and the next molecule, like that. So for a brief moment, the air molecules are together and then they are released. So just like a pressure wave or like a sound wave, the air molecules are coming closer together, forming a dense region and a less denser region, or simply a dense region and a rarer region. So the molecules will be oscillating to and fro. That is, it will be traveling parallel and then back. So as the wave is progressing, the molecules or the particles in that particular wave is also moving parallelly to that particular propagation of the wave. So you can see that it progresses as rarefactions and compressions. So what exactly is compressions and rarefactions? So we can say that as particles are oscillating along the direction of propagation of the wave, the air molecules will be compressed together, which means some of the air molecules will be crowded like this, and some region will be blank like this, because there is an absence of particles in one particular region and there is an excess of particles in one particular region. So just to put an imaginary perspective into your minds. So when the molecules are crumbled together, there is more concentration there. So it is known as a compressed region or compression region. And right next to that particular compression region, the molecule just vacated a space, which means that there will be a gap left there, which means there is a rare portion. So that is why the wave will be propagating as compressions and rarefactions. You can also represent it using thick lines and gaps. You can use alternate thick lines and gaps in order to symbolize a pressure wave or a sound wave, which again is a longitudinal wave. Now, since you have already understood what is a wave, what are the types of waves, it is now time for us to deal with the equation of a wave. So, in the previous chapter, we learned one equation, that is A cos omega t plus phi. Just like that, here also we are using a wave function graph, but again, here we are not using cos, instead we are using sine. I told you in the previous chapter also, you can use sine or cos. Here the standard usage is sine, so I'm just going to use the sine graph. So you can actually represent a wave. Let's say y is equal to, so it is propagating in the x direction and the displacement is in the x direction. So I'm going to represent that particular wave which is having an amplitude of a. Then I can say that, okay, the wave will be a sine kx plus or minus omega t plus phi. So this will be the nature of the wave which we are using in this particular chapter. So what exactly is these particular terms? Sir, we understood what is a sine omega t plus phi. That is understood. But what is this kx? It is a new term. So again, this is the standard form of representing a wave. So again, A is amplitude, sine is the nature of the wave, omega t is nothing but theta, that is angular frequency time, and phi is the phase angle difference, or simply how much difference is there between two waves to indicate all that. These are there. But what is kx? So we are going to discuss what these individual terms are so that you can refresh them and so you can actually remember these terms for future use. So k is actually known as a wave constant or a wave number, and x is just symbolizing, okay, the wave is progressing in the x direction. You can also use kz, you can also use ky, depending on which direction the wave is propagating to. So kx just symbolizes that, okay, the wave is traveling in the x direction. K is a constant and it has a definite value. I'll discuss that very shortly. So again, this particular equation, that is y is equal to a sine kx plus or minus omega t plus phi, is representing a wave that is progressing or a wave that is moving, or we can just call it as a traveling wave, or it can also be called as a plane progressive wave. So it can be called as a plane progressive wave or simply a traveling wave. That is a wave that is in motion. So we're going to discuss the individual terms right now. So this particular term, that is kx plus or minus omega t plus phi, this entire term inside the bracket will give you the state of the wave, or simply here it is known as the phase of a wave. It gives information to which what state the wave is actually in. So what that particular information retains is that what state is that particular wave in. Just like we define the state of a system. Is it solid? Is it liquid? Is it this much? Is it this much? Like that, we can also describe the phase, that is the state of a wave. And that particular information will be given by the quantities that are listed inside this particular bracket. So again, this will give the state of motion of a wave that is at position x, or simply if it is traveling in the x direction, it will give the position at x. If it is traveling in the y direction, at y. In the z direction, it will be given in the z direction. You just have to focus if it is x, y or z here. Now again, we know what frequency is. Frequency is nothing but the number of oscillations that is repeating. Or simply we can say that it is the number of oscillations per second and it is related to the time period in this particular manner. That is, frequency will be equal to 1 by time period. You already know that. Now, what is angular frequency here? That is omega. So, angular frequency omega will be related to the time period by the equation 2 pi divided by t. Because it is a wave function, we can define omega, that is the angular frequency, as 2 pi by t. Or simply you can also write it as 2 pi mu. This is linear frequency, this is angular frequency. Angular velocity and angular frequency have the same symbol, but again here it is angular frequency, and the relation between angular frequency and linear frequency, you already know this, but again is given by 2 pi mu or 2 pi by t. This is the relation between angular frequency and linear frequency. And finally, I told you this particular k, it is known as a wave constant or simply a wave number, and it also has a definite value, and it is given by 2 pi divided by lambda. So 2 pi divided by lambda will give you the wave constant or simply the wave number. And lastly but not leastly, phi, again phi will give you the phase angle difference. So is a wave lagging or leading behind another wave? That particular information will be given by the phase angle, that is indicated as phi. And again, why is there a plus or minus sign here? There is a plus or minus symbol there because if both of these quantities are positive in nature, or if both of these quantities are negative in nature, then we say that the wave is traveling in the negative direction. That is, if kx plus omega t or minus kx minus omega t, if that happens, then we say that, okay, the net displacement of that particular wave is in the negative direction. So if both are positive or both are negative, it is traveling in the negative direction. If one is positive, if kx is positive and omega t is negative, or if kx is negative and omega t is positive, then we say that the wave is traveling in the positive direction. So that is just a trick to figure out where the wave is actually traveling to. Again, it is not that much important, but it is very good to know. Now, the only thing you have to know is the speed of a wave. You already know what is the displacement of a wave, that is given by lambda. And you already know what is the angular frequency, what is the crest, what is the trough, what is the propagation, what is the wave equation, all that. Now it is time to know what is the velocity of a wave or simply speed of a wave. Now, velocity is generally given by displacement divided by time, right? Displacement, rate of change of displacement gives you velocity. Now, in the case of a wave that is propagating, we slightly alter it and we say that, okay, displacement for a wave is measured in wavelength, that is indicated as lambda. Lambda is wavelength. So, lambda is nothing but the distance between two crusts or two troughs. That is how much a wave has traveled in 1 second, or simply one cycle of a wave is known as 1 lambda, or simply the distance between two crests or two troughs is known as 1 lambda. That is how much the wave is linearly displacing. So, linear displacement of a wave is indicated as lambda, which means instead of displacement, here we are going to write lambda, and instead of time for a wave, it is time period. So, we are going to indicate it using t. So, we have speed of a wave given by lambda by t. So, again, you know that 1 by t is equal to mu. So, you can also write this particular equation, that is v is equal to lambda by t, as lambda into mu. So, you have either lambda mu or lambda by t as the equation in order to find the velocity or simply the speed of a wave. So, as I mentioned earlier, v is equal to either lambda by t or lambda mu. Is it over yet? It is not over yet, because we know that the equation of wave constant or simply wave number is given by 2 pi divided by lambda. So, again, if I shift these, then I can say that lambda will be equal to 2 pi divided by k, right? Now, if I substitute this in terms of these equations, I have one more equation that can be written down. So, I can substitute this particular equation here. Then I can say that v is equal to, instead of lambda, 2 pi divided by k, and there is a t here. So, we have one equation like this. Now again, instead of mu, we can also substitute one more equation we learned, that is in terms of angular frequency. Omega is equal to 2 pi mu, or mu is equal to omega by 2 pi. Omega by 2 pi will be equal to mu. So you can substitute this equation also and substitute it here. So you get another equation, that is V will also be equal to, instead of lambda, we have 2 pi by k into omega by 2 pi. So omega divided by 2 pi. So 2 pi and 2 pi cancels. You have omega by k, which is equal to V. So again, you have two more equations you can use to find out what is the speed of a wave. So again, you need to know three more equations that is defining speed, and you don't have any derivations for these. So I'm just going to give it to you directly. So if there is a stretched out string, like a stretched out rubber band or a guitar string, and if you pluck it, there will be waves that is forming. So in those particular waves, what is the equation to find out the speed? So again, the equation is V is equal to T by mu. So what is T by mu? So T is actually tension here on the string, and mu is something known as mass per unit length of the string. So what is mass per unit length of the string? Again, that is just the mass of the string divided by the length of that particular string, and that will give you the value of mu. So this particular equation, V is equal to T by mu, where mu is equal to m by L, mass of the string by length of that particular string, will give you what is the velocity of wave in that particular string. And again, in solids, it is given by the equation V is equal to root of y by rho, where rho is nothing but density. Rho is the density and y is the Young's modulus. Y is the Young's modulus, which you have already learned in the chapter, that is mechanical properties of solids. And again, for fluids, same equation. The only difference is that instead of Young's modulus, you're going to use bulk modulus B. So again, the ratio of bulk modulus to its density in the square root will give you the velocity of a wave in fluids. So that is all for now. That is discussing about the introductory class of waves, and I'll be back with more equations and derivations regarding wave functions. So until then, thank you.